10 a.m. press conference, which we're calling Catching Lightning in the Act. We'll have 3 speakers and then open the floor to questions. Our speakers are Joseph Dwyer. He's a professor in physics in the Physics and Space Sciences Department at the Florida Institute of Technology in Melbourne, Florida. Dustin Hill, he's a graduate student in the International Center for Lightning Research and Testing, Electrical and Computer Engineering Department at the University of Florida, Gainesville. And Megan Schall, she's a graduate student in Physics and Space Sciences Department of the Florida Institute of Technology in Melbourne, and they'll be speaking in that order.
Well, good afternoon. So I'm going to be talking about the first X-ray images of lightning. So this is what lightning looks like optically. So this is what how we're used to seeing lightning. This is actually rocket-triggered lightning that's made at the UF Florida Tech International Center for Lightning Testing and Research. So this work is also, I want to just mention, is collaboration between Florida Tech and the University of Florida. Just a little background. The experiments here is a picture of the ICLRT, commonly referred to as Camp Blanding. This is a Google Earth photograph. It's a 1 kilometer by 1 kilometer site. It's well instrumented for measuring lightning. This is one of the premier lightning research facilities in the world. One unique thing about this facility, it's just one of a handful of facilities in the entire world where we can actually trigger lightning. We can make lightning by launching rockets into thunderstorms. The launch tower is right here in the middle of this facility. Just a little bit of background. Scientists only recently discovered that lightning emits X-rays. This is actually amazing when you think about it. I mean, it's been 250 years since Franklin's kite experiment, and only recently, just within the last decade, 8 years ago, we discovered that lightning emits X-rays, and actually emits a lot of X-rays. It's a part of what lightning does. And we're still trying to understand how it emits X-rays and what this all means, and also what the X-rays can tell us about lightning. And this is this sort of shows you what the data has looked like so far, what we've been dealing with. So this shows you X-ray data from lightning. Now, I don't expect you to look at this and understand what this means. It looks kind of like an EKG or something like that. But this is the data we've been dealing with. There's squiggles on a plot. And this gives us a lot of information about how the X-ray is emitting lightning, but there's also a lot that we don't know. For example, where exactly are the X-rays coming from? And again, this is a photograph of the rocket-triggered lightning that we make. So what are the big questions that we're trying to answer? Now these are actually, you'll notice, these are very simple questions. These are not really technical questions I have to spend 5 minutes sort of leading up to. They're very simple, so how does it work kind of questions. So how does lightning get started inside of a thunderstorm? That's actually a mystery. We don't understand that. How does lightning move? How does it get from the thunderstorm down to the ground where it could hurt or even kill people? We really don't understand that very well. We don't understand the details. We don't understand the physics of how that works. And then how does it, when it gets close to the ground, how does it strike objects? It's really not understood at all how it chooses to strike one object or the other. It's called the attachment process. And then finally, more relevant to this talk, is how does it actually emit X-rays? Lightning is too cold to emit X-rays. It may seem hot. It's about 50,000 degrees Fahrenheit, which may seem hot to us, but in terms of X-ray temperatures, it's downright frigid. So if it's emitting X-rays, which it does, it has to be through something unusual. And finally, we know that it emits X-rays, so do these X-rays play any role in questions 1 through 3? Since we're struggling to understand these questions, to answer these questions, maybe the X-rays are a missing piece that will give us new insight, for example, to how lightning moves. And then finally, I mean, these are all good scientific questions, but really, if you ask me what I really want to know, I want to know what lightning looks like in X-rays. And so I don't want to just see squiggly lines. I actually want to see an image, so I can visualize what's going on, and that's sort of one of the main points here. For the first time, we're going to get a glimpse of what lightning looks like seen in the X-ray emission. So how do we do this? Well, this is actually a very tricky thing to do. Okay, lightning is hard to measure. Okay, it's not predictable. You got to know when and where to point your camera. X-rays are tricky to measure. It's not just like you can't just go get a Nikon camera and point it. You need specialized instrumentation for measuring X-rays. And then lightning is very, very fast. Things are over in a millionth of a second. And so you have to have something that's also very quick. And so you can't just go buy a camera and point it out at lightning and get X-ray images. It's something you have to make specifically for this purpose, for measuring X-rays from lightning. And that's what we did at Florida Tech. And my graduate student, Megan Shaw, at the end, built this camera at Florida Tech, and then was deployed working with UF. So this shows a schematic of the camera. It's a pinhole-style camera. A pinhole camera is a real camera. It makes real images, but you can't use lenses or mirrors with X-rays. You have to do something different. And so there's what I call a pinhole. It's actually 3 inches in diameter. If you have a camera, cameras aren't entirely made of glass, right? You can't have light coming in through the sides. The same is true with X-rays. You don't want X-rays coming in through the sides of your camera, so the whole thing has to be shielded with heavy lead. And this whole camera weighs about 1,500 pounds, most of that in lead. It has half of an inch of lead. We also added in a half an inch. So an inch of lead, you're basically required to shield out the X-rays from the lightning except through the pinhole. Then we have a detector plane here. This camera has 30 pixels, which doesn't sound like a lot, but when you consider that they're recording at 10 million frames a second for 2 seconds, that's actually a lot of data. And that's the kind of rate speed that you need to capture lightning. So here's a photograph. This was taken by Dustin at Camp Blanding. This shows the X-ray camera here. It's about the size of a refrigerator. It's pointed above the rocket launch tower. So when a thunderstorm comes overhead, we're going to launch small rockets with wires behind them into the thunderstorm, and that will bring down the lightning. That will trigger the lightning. So we're looking at the space above the tower. And so when I show you the images, it will be in this space up here above the tower. So here we are all ready to go. And here we go. So this is actually the world's first X-ray image of lightning. And this shows about 5 millionths of a second. I've shown, so this is looking at the space. Here's the tower that I just showed, drawn in. And I'm also drawing in where the lightning was. From optical measurements, we know where the lightning was at that time. So that's what the yellow line is. The lightning was right here. And you can see the glow of X-rays. So we're not making X-rays and shining it at the lightning. The lightning is making the X-rays itself. It's glowing bright in X-rays, and that's what we're recording. And everything you're seeing, there's almost no background. So everything that you're seeing here that's not black are real X-rays coming from the lightning itself. And you can see most of the X-rays are coming from along the lightning channel. And there's the tip of the lightning right now as it's coming down from the thundercloud. And most of the X-rays are coming from the vicinity of the tip of the lightning. Now I'm going to move to the next frame, which is 1 millionth of a second later. And that's what it looks like now. So now the lightning's moved down, struck the tower, and now most of the X-rays are coming from the strike point. And that's glowing very bright. We also find that we're getting this diffuse glow all around. All this is real coming from the lightning. These are actually penetrating gamma rays. These are gamma rays that go right through a half of an inch of lead and a quarter inch of steel. So this is what lightning can do. It can shine so bright in gamma rays at the end that a camera with a half an inch of lead just becomes transparent to them at the end. So since this takes a sequence of frames, one every 10 millionth of a second, I can string them together and make a movie. This was another triggered lightning flash that we recorded. This entire movie, I'm going to loop it, but the entire sequence lasts just 2.5 millionths of a second, 2.5 microseconds. And this is showing lightning at 10 million frames a second. Now what you're going to see is I'm going to show also the lightning propagating down as measured by electric field measurements. We know where the lightning was, so you'll see the X-rays coming down with the lightning. And these X-rays, this source coming down, we're going to see in X-rays, is moving at 1/6 the speed of light. So something moving this fast would go from the Earth to the Moon in less than 10 seconds. So this is how fast this whole thing's going. Here we go. So you can see the X-ray source is tracking the lightning coming down. Okay, I can just show a few frames of this movie. And so this is actually sort of what Superman would see. So Superman has X-ray vision. So how would Superman see lightning if he could look up and see lightning? So each one of these frames, again, is taken 1/10 millionth of a second. And you can see here's one frame right where the lightning tip is. That's where almost all the X-rays are coming from. I'm going to leap ahead a few frames, 3 frames of this movie, and you can see a little bit more clearly that most of the emission, again, a little bit diffuse, is coming from the area of the lightning tip, stepping through again, and then finally the big sort of bang at the end where it attaches to the tower. A lot of emission from the strike point with all these penetrating gamma rays. The camera, again, just becomes transparent to gamma rays at the end. Okay, so let me just sum up. So we built the world's first X-ray camera for measuring X-ray images of lightning, actually movies as well. We recorded 4 lightning flashes during the summer. This was just deployed a few months ago at our lightning facility. We can very clearly see that the X-ray source descends with the lightning at up to 1/6 the speed of light. We see large bursts of gamma rays produced by the lightning when it strikes. And then finally, I want to stress that in science, whenever you have a new tool for looking at something, you usually make big discoveries. You learn new things. You know, Galileo's telescope. This is a new way of looking at lightning, and so we're already learning new things. So thank you very much.
Can we dim the lights slightly, please? Thank you. So good morning. My name is Dustin Hill from the University of Florida Lightning Research Laboratory. The title of my talk today is High-Speed Video Observations of a Natural Lightning Step Leader. The video data that I'm going to show later in the presentation was acquired during June of 2010 at the International Center for Lightning Research and Testing at Camp Blanding, Florida. The ICLRT, as we abbreviate it, is a facility jointly operated by the University of Florida and the Florida Institute of Technology in an effort to study the physics and effects of both natural and rocket-triggered lightning discharges. The ICLRT is equipped with around 80 ground-based measurements and cameras to study both the energetic radiation, optical, and electromagnetic radiation from lightning. So we have 3 fundamental lightning questions that we're attempting to answer at the ICLRT. First, how does lightning initiate in the cloud? Second, how does lightning propagate through virgin air? And third, how does lightning attach to ground-based objects? In this presentation, we're going to focus on the second point, which is how does lightning propagate through virgin air. Before actually showing some of our video data, I'd like to give a brief general description on the negative cloud-to-ground discharge process. In this figure, time progresses from left to right, and we've color-coded the different discharge stages for easier interpretation. In step 1, we have a negative air breakdown that moves out of the cloud towards the ground at around 10 to the 5th meters per second. This breakdown we term as a step leader. The step refers to the basic discontinuous nature of the discharge process. Negative charge is deposited along this channel as it moves towards ground. In step 2, as the step leader nears the ground surface, one or more upward positive discharges can propagate from the ground in response to the negative moving step leader. And as they connect, we call this region the attachment process. In step 3, after the connection is made between the negative moving step leader and the upward propagating positive leader, a current wave moves up, neutralizing the negative charge on the channel. This is what we call the return stroke. It moves at around 1/3 of the speed of light on average, and it's actually what we visibly perceive as a lightning strike. Typically, after the return stroke, there's still an ionized channel, and oftentimes, after some tens of milliseconds, a second air breakdown propagates out of the cloud, down the existing channel, and comes towards ground. This moves significantly faster than the original step leader at around 10 to the 7th meters per second. We refer to this process as a dart leader. After the dart leader makes contact with ground, a second return stroke propagates up the existing channel. This process can repeat up to 20 or more times, more typically 3 to 5 times, and is actually what we perceive as the flickering in a natural lightning strike. In this talk today, the video I will show revolves around the first stage of this discharge process, which is the actual negative step leader as it descends from the cloud. Some basic photographic setup. The camera is a high-speed camera called a Photron SA 1.1. This camera was operated at a frame rate of 300,000 frames per second, which gives an exposure of only 3.33 microseconds. The estimated field of view is roughly from 25 meters to about 345 meters above ground level, and an estimated distance to the actual lightning channel of about 1 kilometer. At this distance, we have a spatial resolution of about 1 meter per pixel. And at right, I've just shown an image of the actual camera. The actual channel imaged was one branch of a natural cloud-to-ground lightning. The channel itself actually terminated out of the field of view, but the branch was imaged. At left, I've shown a wide-angle, high-definition video frame of the full branch. In the white box, which I've shown with a square, is what we believe is the actual image captured by the high-speed video camera, which is shown at right in a full-frame image. The high-speed video frame is, like I say, goes from about 45 meters to about 345 meters above ground, and the actual channel image covers about 160 meters. In the high-speed video image shown, you can see all of the fine branching structure. I'm now actually going to play the video, first at 30 frames per second, or an actual speed of 100 microseconds per second. The actual bright re-illumination you see at the end is due to the actual ground detachment of the channel out of the field of view. I'll play it once more. I'm now going to play the video at 5 frames per second, or a factor of 6 slower than what you just saw, at an actual speed of 16.7 microseconds per second. At this frame rate, you can actually distinguish the individual leader steps or the propagation mechanism by an isolated brightening of the leader tip as it moves down, followed by an upward propagating luminosity wave which illuminates the channel for some tens of meters from the actual leader tip. In total, around 80 individual leader steps were imaged during this discharge. And the return stroke re-illumination. By stepping through this video frame by frame, we're able to measure such statistics as the actual length of each step, we're able to measure the time between steps, and we're able to construct essentially a sequential map of the step formation process. In doing this, we get a better idea of the actual propagation mechanism of the step leader. So to conclude, we've shown the fastest frame measurements that have ever been taken at 300,000 frames per second of a natural negative step leader. We've also shown that the propagation mechanism for natural negative lightning step leaders is very similar to what has been demonstrated in prior laboratory spark experiments and in rocket-triggered lightning discharges. Finally, we have shown that the actual time between steps, what we call the interstep interval, and the actual step lengths obtained from our video data are generally shorter than those statistics that have been measured from previous optical experiments of step leaders, and are in much better agreement with propagation through preconditioned channels. Thank you.
Thank you. We will now take questions from journalists.
Hi, I have a couple of, Carrie Payton Dahlberg, freelance. In the image, in the video of the X-ray images coming down from the lightning, at about what degree was the camera pointed toward the horizon, and what was the tower? Was it the rocket launch tower?
Yeah, so the camera was just about 45 degrees from horizontal, and yes, that was the rocket launch tower.
Rick Lovett, freelance. Two questions, one for each of you. First of all, so it comes down in steps. Do we understand anything about why it goes jerk, step, 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 step?
Very little, actually. So where lightning research is right now, we're very good at the phenomenology. We're very good at saying what lightning does, but not so good at saying how or why it does it. There's a hint from laboratory sparks where you can also see the stepping. And a big question is, can you sort of extrapolate something in the laboratory that's, that big to something that's, say, 50 yards long? So there's a huge difference in the size of steps. And so a big question is, can you sort of take measurements in the lab and say, yes, that applies to lightning? The basic physics, how and why lightning steps, we really don't know.
Okay, and the other thing is, on the X-ray, if I understand correctly, it came down at a sixth of the speed of light, but that's not 10 to the fifth meters. So where does that fit into the visual image?
Yeah, so that was a dart leader, a type of dart leader that was coming down that we were seeing.
But it was going a lot faster than the one we just saw visually.
Yeah, that was a stepped leader that you were seeing, the image, and the X-rays was a dart leader. Do you want to expand?
Yeah, the video that I showed here is moving through virgin air. It is not moving through a preconditioned channel and moves around 2 orders of magnitude slower than what we showed with the X-ray images, which is moving around 10 to the 7th meters per second, roughly.
This is Alex Whitsey with Science News, and I had two questions for Dustin, actually. Sorry, I'm back here. Can you talk a little bit more about the circumstances in which your video was taken? Was it, what month was it? What day was it? What kind of, yeah.
The video was acquired on June 18th of 2010. The actual camera was configured for imaging rocket-triggered lightning discharges, and fortuitously triggered on a natural lightning branch that happened to cross the field of view and fortunately propagated somewhat vertically within the field of view for around 245 frames.
Was it like just a big thunderstorm that was coming through and it happened to catch it?
Yes. And we actually had a triggered lightning discharge that day as well.
Okay. And where can we get, if we want to obtain the video and images, how could we get a copy of that plus the X-ray lightning image?
At the present time, we are not going to disseminate the video I showed today. It's still being analyzed and will soon be published. We are willing to disseminate some more general videos that we have acquired of various lightning processes.
You can have all the X-ray images. I'll make them available at the end.
Thanks.
Paul Doherty from the Exploratorium, and I was wondering, so what were the lengths of the step leaders that you measured, and what was the interstep timing?
The interstep times were roughly from about 13 to 15 microseconds, and the steps were roughly 5 meters in length, both of which are significantly shorter than what has been measured optically historically.
And then for Joseph, so you showed the picture correlating the visible leader with the X-ray leader, and yet that X-ray camera is 10 mega shots per second. How did you do the correlation with a much slower camera on the visible leader?
Okay, there's two ways we did that. One was just using a couple frames of the high-speed video and interpolating, but the movie was done with, Dustin made these measurements using electric field measurements, which are very precise. So he was able to sort of pinpoint where the lightning was, measuring the steps as it came down, and then we just connected the dots. Did you want to say anything more?
That's more or less.
Thank you.
Bert Schwarzschild, Physics Today. I have one question about the X-rays and then about the virgin air. Before you showed the pinhole camera images, I saw something that might have been a line spectrum. Did you actually get energies of specific lines?
Yeah, okay, so what you were seeing was the plot I showed the bursts of X-rays. That was sort of like what an oscilloscope would record. And yes, we can measure the individual X-ray energies, and this is something we've been doing for several years. And yes, the typical energy range of X-ray emission from lightning is several hundred keV up to a few MeV. And so this is, for those of you who aren't familiar with this scale, a few times typical chest X-ray energies, up to maybe 10 times that.
And then these negatively charged leaders through virgin air, is it, I mean, presumably the virgin air is locally electrically neutral. This is electrons migrating from the cloud down, or?
Yeah, the step leader carries a net negative electric charge. So you've got a negative charge distribution moving down with some distribution over the leader channel with a higher enhanced electric field at the actual tip of the leader, which is also producing the X-rays we see from natural negative leader steps. And it propagates downward towards Earth.
Hi, Boston Hunt, economist. A question for Mr. Dwyer.
Yes.
You mentioned that lightning actually was too cold to produce X-rays.
Yes.
And now you see X-rays coming from the tip. Are you prepared to speculate that the tip is actually very hot? Or do you think something else is going on there?
Yeah, it's something else. It's a non-thermal process. So in order to get X-rays, you need electrons moving very, very fast. So the electric fields are so incredibly strong in front of the lightning that it can accelerate electrons through air up to almost the speed of light, and those electrons are what emit the X-rays.
So did you expect the X-rays to come from the tip?
That's the logical place. I mean, if you're going to, we really didn't know. I mean, no one's ever really measured where they were come from. It could have, I mean, some of the possibilities, it could have been a big diffuse glow just from that area, or it could have been more concentrated at the tip, or there could have been sort of sending out all these branches out in front. It could have been coming from all of those. We really didn't know which of those possibilities, and so it's interesting that it's mostly coming from the tip.
Just to follow that up, so these are like synchrotron X-rays. Is that
Well,
right?
it's Bremsstrahlung
Right,
is the mechanism,
Yeah,
which is
okay.
German for braking radiation.
Yeah. Just one of sorry, it's Jonathan Amos from BBC. One of approach. I mean, you're producing lightning kind of artificially. Does that in any way impinge on your ability to get at the natural mechanisms?
As far as we can tell, the rocket-triggered lightning, if you consider just the subsequent strokes, the ones after the step leader, they seem to be exactly the same as natural lightning leaders. And we have verified that also with the X-ray measurements. So we can measure X-rays from both triggered lightning and natural lightning. And as far as we can tell, looking at all the pulses, the energies, the timing, it seems to be identical. So we believe that by studying triggered lightning, we're learning something about natural lightning. But the advantage of triggered lightning, it's like a laboratory experiment. We can repeat it. We can do it again. We can change the setup. And so this has really helped us move forward in this area of science, is we now have a repeatable experiment that we can do.
Davide Castelvecchi from Scientific American. I seem to recall maybe from high school science that lightning was supposed to, the plasma formed because of the propagation of a mechanical shock wave. Is that something I'm misremembering, or is that something that has been superseded by new discoveries?
You mean how does lightning actually move, or how does it?
How does the plasma form? How does the channel
Okay, how the channel actually forms up inside the thunderstorm, nobody knows. It's actually a really big mystery. The electric fields never seem to be big enough to actually make a spark, and so that's an entire other area of research that a lot of people like us are working on. Once lightning gets going, you form a hot channel. The hot channel, I mean, it's a conductive channel, so it carries the charge, concentrates it at the tip, and produces a big enough field to cause electrical breakdown at the tip. So you have electrical breakdown going on in front of it, which then feeds the channel with current, which keeps it hot, which allows it to propagate, which allows it to break down the air. And it's a pretty neat thing that it manages to sort of balance all this and keep it going for miles.
And a follow-up question. This process happens at 1/6 of the speed of light, right?
This was the dart leader, and it was actually a rather fast dart leader that we recorded. So most dart leaders are about, say, a 20th the speed of light. This particular one that we recorded with X-rays was about 1/6 of the speed of light. So that was, yes.
But am I wrong that the human eye can see the lightning as it forms, and if so, is it probably one of the fastest things that our eyes can temporally resolve?
You couldn't see the dart leader, but you can see step leaders propagate. For example, spider lightning, which maybe some of you have seen, it sort of moves along and branches underneath the clouds. That does move slow enough, about 1 × 10⁵ meters a second, that if it moves across the horizon, you can perceive that motion. And yeah, I'm not exactly sure if it's the fastest thing we can see, but I'm willing to bet if it's not, it's pretty close to the fastest thing.
Rick Lovett again, freelance. I have a question about the triggering process. So you're firing a rocket up there. Did you say you have a wire on it? Is that what brings the lightning back down?
Yeah, the rocket is equipped with a spool of Kevlar-coated copper wire that is about 700 meters in length, 30-gauge Kevlar-coated copper. And as you shoot the rocket up, the wire unspools turn by turn. Typically, the discharge is initiated at a height from anywhere from 200 to 400 meters.
Are there any additional questions? Well, thank you very much for participating. Thank you for attending. Our next press conference will be at 11.
Thank you.